What's up, everybody, and welcome back to OpenStax Algebra and Trigonometry, Chapter 6, Section 6, Exponential and Logarithmic Equations. Let's do it. So when we talk about exponential equations, there's kind of two general roots. So the first thing is, let's say we have 2 to the x, and that's what we mean by an exponential equation, right? The variable is in the exponent. We have 2 to the x equals 8. Your first objective is to try and get the same base for both sides of the equation. So for example, that's 2 to the x. I can write 8 as 2 to the third. Hence, I then know that x equals 3. The other way that you might solve it is, let's say you have 3 to the x equals 10. Now, in this case, I can't get these to both be powers of 3. So what I would have to do then is use logarithms, right? Then you take the log of both sides. And the reason why this is cool is because this allows you to bring that exponent down in front as a coefficient, like so. And then once you get to this point, you can divide both sides by log of 3, boom, like so, cancel out, and you would get your answer for x. So that's how you do it, done. So the one-to-one property of a logarithm can be used to solve an equation when you can consolidate each side of an equation into a single logarithm. So let me give you an example. Let's say we have log of 2x plus log of 7x. And by the way, this is going to be base 10, right? When there's no base written, equals log of 56. So in this case, what you could do is, since these have the same base, 10, 10, you can take that addition and you can consolidate by multiplying the argument. So then we have log of 14x squared equals log of 56. So when you can do this, you can then just set these two arguments equal to each other and solve for x. 14x squared equals 56, divide by 14. X squared equals 4, hence then we get x equals 2. And if you can't consolidate into a single logarithm, then it cannot be used. So there's your answer, done. So for this one, we're going to solve by making everything into the same base. And what I see is 16, 4, and 64. And these can all be written as powers of 4. So let's do that. 64 is 4 times 4 times 4, which is 4 cubed. This is 4 to the 3x. It's already a 4. And then 16 is 4 squared. So check this out. Now what I can do is I can use my exponent rules. When the same bases are multiplying, we just add those exponents. So it's 4, 3 to the 3 plus 3x power equals 4 squared. Now when we have the same base on the left and the right, we can just set these arguments equal to each other, right? So we can say 3 plus 3x equals 2. Subtract 3 from both sides like so, and we get 3x equals negative 1. Last step, we divide by 3, boom, boom, and we get x equals negative 1/3, boom, done. So for this one, we're going to get everything to be the same base, and what I'm seeing here is 2, 1/4, and 2. These can all be nice powers of 2. So right off the bat, I've already got 2 to the negative 3n. And then 4 is really 2 to the negative 2, right? Because a negative exponent means it would be 1 over 2 squared. 2 squared is 4. So that is simply another way to write 1/4 equals 2 to the n plus 2. Now, since these are multiplying, we can add the exponents, so it becomes 2 to the negative 3n plus negative 2, or minus 2, equals 2 to the n plus 2. Now that we have the same base, we can just set these two equal to each other. Now I'm going to subtract n from both sides. Boom, negative 3n minus n is negative 4n, and then I'm going to add 2 to both sides as well. That's going to cancel out. Then we get 4. Divide both sides by negative 4, n equals negative 1. Boom, done. For this one, we're going to try and get everything down to 6, because 216 is 6 cubed, 36 is 6 squared. So on the top, we have 6 squared, and that's to the 3b power, over 6 squared on the bottom, and that's to the 2b power, equals, and then 216 is 6 to the 3rd power, and then that to the 2 minus b. Now I'm going to use my exponent rules. Since this is kind of hanging or floating outside that parentheses, these two are going to multiply. Same with these guys. So we get 6 to the 6b over 6 to the 4b, and this equals, this is going to multiply and distribute like that. 6 to the 3 times 2 is 6 minus 3 times b, which is minus 3b. Okay, and then since I have division on the left-hand side and there's the same base, I can just rewrite this as subtraction. The top exponent minus the bottom exponent. And now we have everything consolidated to a single base. Now we can just set these exponents equal to each other. So we have 6b minus 4b equals 6 minus 3b. 6b minus 4b is, of course, 2b equals 6 minus 3b. Then I'm going to add 3b to both sides. That's 5b equals, that's going to cancel out 6. Last step, We divide both sides by 5. B equals 6 over 5. Boom, done. So for this one, I can't make these into both the same base. So what I'm going to use is I'm going to use logarithms, okay? So to get that exponent down, I'm going to take log of both sides. And since I can take any base I want, I'm going to choose base 9, okay? Now, the reason why that's nice is because log base 9 of 9 is just going to cancel out to 1. And then using my exponent rules, I'm allowed to bring this down. So it's going to be x minus 10 times 1, which is just x minus 10. And then on this side, I'm taking log of 1. Now, log of any base of 1 is always 0 because this is saying 9 to what power is 1, 10 to what power is 1. It's all 0. So now we have 0. Last step, I'm going to add 10 to both sides, and I get x equals 10. Boom, done. So for this one to solve, we're going to have to use logarithms, but first I'm going to isolate that e. So I have e to the r plus 10 equals, I'm going to add 10 to both sides, negative 32. So now I need to solve for this exponential variable, right? And to get at that variable, I need to use a logarithm to kind of bring it down. So I'm going to take natural log of both sides. Now that's arbitrary, right? I could take log base 10, log base 100. It doesn't matter. The reason why I'm choosing natural log or log base e is because this is e, right? And it's just going to make it easier. I'm going to show you why in a second. Also have to take natural log of negative 32 as well. So natural log of e basically just cancels out and allows you to bring this exponent down. So it ends up being r plus 10 times 1, or just r plus 10 equals this. But there's something interesting that's happening here. We're trying to take a logarithm of a negative number. Negatives, however, are outside of the domain of logarithmic functions. I can't take natural log of negative 32. That does not exist, which means that there's actually no solution for this one. Done. So for this one, we're going to start by isolating this guy, and then we're going to take a log to bring that exponent down. So first I'm going to add 7 to both sides like so, and I get negative 8 times 10 to the p plus 7 equals negative 17. Then I'm going to divide both sides by negative 8, and I get 10 to the p plus 7 equals 17 over 8. Then I'm going to take log of both sides. That's going to be how I'm going to get that exponent down. So I'm going to take log of 10 to the p plus 7 equals log of 17 over 8. Now again, the base of this log is arbitrary, but I'm going to choose base 10, your typical log, because we're taking log of 10. And when you take log of a base of that same argument as the base, here log base 10 of 10, these guys just basically cancel out and that exponent just drops down. And so that's really nice. So now I have p plus 7 equals log of 17 over 8. Last step, I'm going to subtract 7 from both sides. P equals log of 17 over 8 minus 7. Boom, done. So for this one, we're going to start by isolating e. So I'm going to subtract 6 from both sides, and then I get e to the negative 3k equals 44 minus 6, which is 38. Then I'm going to take the natural log of both sides. And the reason why I'm choosing natural log is because I have e to an exponent with a variable in it, right? So if I take natural log of e, it's going to essentially cancel out, and we'll be left with that nice exponent. So I'm going to do natural log of both sides. We're going to bring this down, and like I said, this will cancel out. So now I have negative 3k equals ln of 38. Last but not least, I'm going to divide both sides by negative 3, and k equals natural log of 38 divided by negative 3. There's your answer. Done. For this one, we're going to start by isolating that exponential variable. So the first step is minusing 2 from both sides. Then we have negative 6e to the 9x plus 8 equals negative 74 minus 2 is negative 76. Then we're going to divide both sides by that coefficient of negative 6, like so. And then we have e to the 9x plus 8 equals 76 over 6, which can be reduced, divide top and bottom by negative 2. We get 38 over 3. Now we need to get this exponent down. So I'm going to take the natural log on both sides, because this will allow me to bring it down by my power rule for logarithms. And then ln of e is 1, because a log base something of that same something, meaning log base 10 of 10 or log base 5 of 5, that's always going to be 1. So log base e of e is going to go to 1, and then we're just left with that nice exponent after it's brought down. 9x plus 8 equals ln of 38 over 3. Last two steps, we're going to subtract 8 from both sides. We get 9x equals ln of 38 over 3 minus 8. Last step, divide both sides by 9. We get ln of 38 over 3 minus 8. all over 9. There's your answer. Done. This one is what's called a quadratic in disguise, right? It's something squared and then a constant. So you really want to think about it in terms of factoring. And you imagine, normally it'd be xx, right? X squared and stuff like that. But here, it's whatever's in the middle term that's going to go in the front and the front here. So it's going to be e to the x. And this makes a lot of sense because e to the x times e to the x is e to the 2x, okay? Then we just go with our normal factoring. What two numbers multiply to negative 132 add to negative 1? That's going to be negative 12 and positive 11. So now you can see, since this is factored, we have two different equations because we're trying to get this to 0. So that means all I care about is when this binomial is going to equal 0 or when this is going to equal 0. So we have two different possible solutions. So here, I'm going to add 12 to both sides. I get e to the x equals 12. Then I'm going to take the natural log of both sides. I'm choosing natural log because we have an e here. So natural log of e to the x, those cancel out to 1, allowed to bring that exponent down, and then we have x equals ln of 12. So there's one solution. Now for the right side, we'd subtract 11 from both sides. E to the x equals negative 11. Now we would take the natural log of both sides again to bring this exponent down. But the problem is I can't take a logarithm of a negative number. It's outside of the domain. So this is a no solution situation. So our only solution is ln of 12. Boom, done. So for this one, we're going to start by subtracting 2 from both sides. And then we've got 10 e to the 8x plus 3 equals 6. Then we're going to divide both sides by 10. E to the 8x plus 3 equals 6 divided by 10, which reduces to 3 over 5. Then we're going to take the natural log of both sides, right? And that's again because I have an e here. So ln of e to the 8x plus 3 equals ln of 3/5 on the right-hand side. This, taking the natural log, allows me to bring the exponent down to the front, and natural log of e is now just 1, so that cancels out. So now we have 8x plus 3 equals ln of 3/5. Then we're going to subtract 3 from both sides, whoops, like that. And then I have 8x equals ln of 3/5 minus 3. And then last step, I'm going to divide both sides by 8. So I have x equals ln of 3/5 minus 3 over 8. There's the answer. Boom, done. So for this one, we're going to start by adding 4 to both sides like so. Then I have 8e to the negative 5x minus 2 equals negative 86. Then we're going to divide both sides by 8 like so. And I get e to the negative 5x minus 2 equals negative 86 over 8, which reduces to negative 43 over 4. Okay. Now we get to this point and we got to bring that exponent down. We got to get the variable down. So I have to take a log of both sides, and I would take natural log because I've got e here. That's going to be the easiest. But you see right off the bat, this will require me to take a natural log on the right-hand side of a negative, and we're not allowed to do that. That's outside of the domain of any logarithm. So can't take a natural log of a negative, which means this is a no solution situation. Done. This one is another quadratic in disguise, and I'm going to factor it just like it was x squared and x. Instead, it's e to the 2x and e to the x. So likewise, I'm going to put that middle term e to the x here and here. And this makes sense because when you multiply them, you add the exponents and you'd get e to the 2x like we see there. Then we're just going to say what two numbers multiply to negative 6, add to negative 1. That'd be negative 3 and positive 2. And now we have two possible solutions when this, meaning e to the x minus 3 equals 0, and when this, meaning e to the x plus 2 equals 0. Now we'll solve both of these. Here I'm going to add 3 to both sides. E to the x equals 3. Then I'm going to take the natural log of both sides, and we get ln of e to the x equals ln of 3. Now I can use my power rule and bring the exponent down, and ln of e is just 1 because a log of a base of that same base as the argument is going to be 1. Log 5 of 5, log 10 of 10, all 1. So then I have x equals ln of 3, and we're good with this solution. And then on this side, we're going to subtract 2 from both sides. E to the x equals negative 2. Then we take natural log of both sides as well. But since this is a negative, we can't take a log of a negative argument. So this is a no solution situation here, which means our only viable solution is ln of 3. Boom, done. So for this one, we're going to rewrite it as an exponential equation, recognizing that when there's no base written, it's really a base of 10. Now, to rewrite a logarithmic as an exponential, it's that base 10 to the power of what's on the other side of the equal sign, aka -2, equals the argument, which is 1 over 100. And by the way, this is a true statement. 10 to the -2 is 1 over 100, but that's how you would state it. Done. So first, to solve this, I'm going to start by dividing both sides by 5. So I have log base 7 of n equals 10 divided by 5, which is 2. Now to convert this into exponential, it's the base of the logarithm to the power on the other side equals the variable. So we would have 7 to the second power, which equals n. And that means n is 7 squared, and 7 squared is 49. So there you go. Boom, done. So for this one, we're going to start by subtracting 4 from both sides to isolate the logarithm. Then I have log base 2 of 9k equals -2. Now, once we have it in this equation format, we can turn it into an exponential pretty easily. It's the base to this power equals the argument. So 2 to the -2 equals 9k. Now, 2 to the -2 is 1 over 2 squared, which is 1/4, equals 9k. Last step, we're going to multiply by the reciprocal of 9, which is 1/9, or divide by 9, same thing. I'll just do it like this because it'll be easier on the left-hand side. So these cancel out. And then I have k equals 9 times 4 is 36. So it's 1 over 36. Boom, done. So for this one, we're going to start by subtracting 10 from both sides like so. And then I have -4 ln of 9 minus 8x equals -4. Then I'm going to divide both sides by -4. And I get ln of 9 minus 8x equals 1. Now I can convert this. And again, I can go by the base to this power is this. So I don't have a base written here, but when it's natural log, we know that the base is e. So it's e to the first power equals 9 minus 8x. Now I'm going to subtract 9 from both sides like so, and I have -8x equals e minus 9. Then we're going to divide both sides by -8, divide by -8, and we get x equals e minus 9 over -8 for the win. And just FYI, in the answers, what they did is they took that negative and they moved it up to the numerator, so they made it a +8, and they made that a +9 and made that a -e. But again, these two are identical, so as long as your teacher doesn't have a strong preference, both of these are good. Done. So for this one, since we're using that one-to-one property, since I have log of the same base on both sides of single arguments, I can just set these two arguments equal to each other. Now I can solve for n. I can add 5n to both sides like so. That's going to cancel it out here. Simultaneously, I'll add 2 to both sides like so. So I get 5n plus 5n, which is 10n equals 8 plus 2, which is 10. Divide both sides by 10, n equals 1. And then just to be safe, you should plug it back in and make sure we get legitimate answers. So if you plug in 1, you get 5 times 1, which is 5 minus 2 is 3. So you have log base 13 of 3 equaling on this side. Plug in 1, 8 minus 5 is 3. Log base 13 of 3 as well. Of course, those two are equal. Verified. Done. So for this one, since we have the same logs on both sides, natural log, we can just set these two arguments equal to each other. Since this is a quadratic, I'm going to use the zero product rule, add 3x to both sides, x squared, and then -6x plus 3x is -3x. Then I can factor out an x from this, right? And I can say x times x minus 3. And then we have two solutions. We have when this zeroes out, which is at 0, and we have when this zeroes out, which is happening when x equals 3. Now, just to be safe, we need to plug both of these back in up here to make sure that they work. One works, both work, or neither work. So if I plug in 0, I get ln of 0 equals ln of 0. But the problem is you can't actually take ln of 0. There's no solution to that. So that's not a viable solution. When I plug in 3, I get ln of -9 equals ln of 9 minus 18, which again is -9. But the problem, once again, there is you can't take a logarithm of a negative either, which means that neither of these are viable. We would say no solution. Done. For this one, we have natural log, natural log, natural log. But the problem is, in order to use the one-to-one property, we have to consolidate these two to be a single logarithm, right? And we can do that because when we see subtraction, that allows us to put that in as a quotient. So it's really ln of x minus 2, that first argument, divided by the second one, which is x. And this now all equals ln of 54. Now I can set the arguments equal to each other. So x minus 2 over x equals 54. Multiply both sides by x. X minus 2 equals 54x. Then I'm going to subtract x from both sides like so. I get -2 equals 53x, because this is a 54x minus 1x. Then we're going to divide both sides by 53 like so. And I get x equals negative 2 over 53. Now to make sure this works, we're going to plug it in up here. So if I have negative 2 over 53 minus 2, that's going to give me ln of some negative argument. And we cannot take ln of a negative number. We can't take any log of any base of a negative. So again, this is not a viable answer. So this is another no solution situation. Boom, done. So for this one, we need to start by consolidating these into a single logarithm. And because there's a plus in between, we're allowed to do that by multiplying these arguments. So we have ln of 9 times x squared minus 10 equals ln of 10. Now that I have single logarithms on both the left and right side, I can now set these arguments equal to each other. So let's simultaneously distribute that 9. We have 9x squared minus 90 equals 10. Then I can add 90 to both sides like so, boom, and then I get 9x squared equals 100. Then I'm going to divide both sides by 9 like that, and I get x squared equals 100 over 9, and then last step, I'm going to take the square root of both sides, and I get x equals plus or minus 10 over 3. So now I need to plug both of these in to make sure they're legitimate. If I plug in positive 10 over 3, I square it, I get 100 over 9 minus 10. That would give you 10 ninths, and so that's legitimate. And because it's x is squared, I would get the same thing if I plugged in negative 10 thirds as well. So actually, both of these are viable solutions. Boom, done. For this one, we're going to start by consolidating these on the left-hand side. And since it's the same logarithm, aka natural log, and we're adding, we can multiply those two arguments. So now it's ln of x times x minus 3, which if you distribute that, becomes x squared minus 3x equals ln of 7x. Now that I have single logarithms on both sides, I can set the arguments equal to each other. X squared minus 3x equals 7x. I'm going to subtract 7x from both sides like so. And then I get x squared minus 10x equals 0. Then we're going to factor an x out of both of these, and I get x minus 10 equals 0. And this gives me two solutions. When this zeroes out at x equals 0, and when this zeroes out at x equals 10. Now we need to plug back in and make sure these are legitimate. I already see an issue with 0 because here I would be taking natural log of 0, which you can't do, right? That's outside of the domain. So 0 is obviously out. Now what about 10? Here I'd take ln of 10, here I'd take ln of 7, here I'd take ln of 70. That's allowed. That's within the domain of a log or a natural log in particular. So the answer is therefore x equals 10, boom, done. For this one, we're going to start by consolidating the logarithms on the left-hand side, and I can do that because they're the same logs and we're adding, which means the arguments can multiply. So we got ln of 7 times 2, which is 14, minus 7 times 4, which is 28, x squared equals ln of 14. Now I can set the two arguments equal to each other. 14 minus 28 x squared equals 14. These will cancel out to 0. I have negative 28 x squared equals 0. Divide by negative 28 x squared equals 0. And of course, the only possible answer for x here must be 0. Okay, but now we have to check and make sure that's legitimate. If I plug it in here, I get ln of 7 plus ln of 2, right? That just goes away, equals ln of 14. And I know that's legitimate. There's no issues. We're not taking logs of 0 or negative numbers. So 0 is the answer. Done. So for this one, we're going to start by consolidating these logs. And because it's subtraction, we can do that because the rule is when you have subtraction of the same logs, you can also rewrite it as a single argument with the first number in the numerator, the second expression, in this case, in the denominator, equals ln of 4. And this is good because now we've got it consolidated. Now I can set the arguments of these two natural logs equal to each other. So let's do that. Now 3 over 3 minus 3x equals 4. Then I'm going to multiply both sides by this denominator. That's going to get rid of it on the left-hand side. On the right-hand side, it's going to be 4 times that, which is 12 minus 12x, right? 4 times each of those pieces. Then I'm going to minus 12 minus 12. We got negative 9 equals negative 12x. Last step, divide both sides by negative 12. We get 9 over 12 because the negatives cancel, and 9 over 12 reduces to 3/4. So now we got to make sure that this is a legitimate solution. If I plug it in here, right here, it doesn't matter. We just have ln of 3, ln of 4. Then it'd be 3 minus 3 times 3/4, which is 9/4. And you can do that. That will not give you 0. That will not give you a negative argument. So this is, in fact, a legitimate solution. 3/4, boom, done. For this one, we're going to start by adding 5 to both sides like so. We have log base 9 of x equals 1. Then I'm going to convert this to its exponential equivalent to solve. So I'm going to say the base to this power equals this. So it's 9 to the first power equals x, which means x just equals 9. There's our solution. Now we're going to graph the left side and the right side as two separate equations in Desmos and see where they intersect. And of course, if we've done it correctly, they should intersect at 9. So here are the graphs of the two equations, and you can see that they intersect just as we predicted at x equals 9. So 9 has been verified, boom, done. So for this one, we're going to start by converting it to its exponential equivalent, remembering that natural log has a base of e. So we say it's e to the second power equals 3x, divide both sides by 3, and we get x equals e squared over 3. And just as a frame of reference, e squared is like 7.3 about. So 7.3 over 3, so it's, a little bit more than 7/3. But anyways, we're going to now graph it in Desmos. We're going to graph this on one side, this on the other side, and then we're going to see where they intersect, and it should be equivalent to this. So here we have the two graphs, and we can see where they intersect is 2.463. And just so you can compare, we got e squared over 3, which is 2.463, so it is verified there. So if we round to the nearest tenth, it's approximately 2.5, boom, done. So for this one, we're going to start by consolidating here these two logs. And when we're adding, it means we multiply the arguments. So we get log base 10, because there's no base, right? Log base 10 of negative 20x equals 2. Now I'm going to convert this to its exponential equivalent, remembering that the base here is 10. So it's the base to that power 10 squared equals the argument, negative 20x. 10 squared is 100. Divide both sides by negative 20. X equals negative 5. Now we're going to graph the left side as one equation, the right side as another one, and see where they intersect. And again, they should intersect at x equals negative 5. So here are the graphs of the two functions, and they do indeed intersect at negative 5. So negative 5 is the confirmed answer, done. So for this one, we're going to start by adding 6 to both sides to isolate that natural log. So now we have natural log of 4x minus 10 equals 6 plus negative 5, which is 1. Now I'm going to convert it to its exponential equivalent, remembering that the base of a natural log is e. So it's e to that power, which is e to the 1, which is just e, equals 4x minus 10. Then to isolate x, I'm going to add 10 to both sides, and then I got 4x equals e plus 10. Last but not least, we're going to divide by 4. Okay, so there's our answer. X equals e plus 10 over 4. Now we're going to graph it in Desmos, and we're going to confirm that the intersection is indeed at this number. So here we have the graphs of the two functions, and this is where they intersect at 3.18. And I put in e plus 10 over 4 here just so you can see that that is the same value, right? Rounded to the nearest hundred, so 3.18. So rounding to the nearest tenth, we can also say 3.2. So there's your verified solution, done. So for this one, we're going to start by just setting these arguments equal to each other because we have the same log on both sides. So we have negative 2x squared minus 7x equals x minus 2. Now I'm going to set everything equal to 0. I'm going to subtract x from both sides and add 2 to both sides. Goodbye, goodbye. So then I have negative 2x squared minus 7x minus x is minus 8x. And then plus 2 equals 0. Then I'm going to divide everything by negative 2 to make it simpler. X squared plus 4x minus 1 equals 0. So now we have a quadratic that's not factorable. So what I'm going to do is I'm going to use the quadratic formula to solve for this, which will be at negative b, which is a, b, and c are those coefficient of those constants there. Negative b plus or minus the square root of b squared, which is 16, minus 4, a is 1, c is negative 1, all over 2a. A is 1, so it's 2 times 1, which is 2. So here, as we simplify, we get negative 4 plus or minus. The negatives cancel out, so it's 16 plus 4, which is 20. So negative 4 plus or minus the square root of 20 over 2, like so. So when you evaluate these in a calculator, you get approximately x equals 0.2 or x equals negative 4.2, okay? So that's what these two solutions will give you. But you can quickly check by plugging them in up here. When you plug in 0.2, you're going to get log of a negative answer. That's not viable. Plug in negative 4.2. Again, you're going to take log of a negative argument. That's not viable. So we're actually seeing that we've got a no solution situation. But now we're going to graph it in Desmos, and we're going to see. And a sign that this is no solution is the left and right side, or these two functions, should never intersect. So as you can see with these two functions, it sure looks like they're never intersecting, right? The red one is kind of in this area. The blue is over here. So there is no intersection. So no solution has been confirmed. Done. So for this one, we've got the logs on left and right side, same bases, which means I can jump ahead and set these arguments equal to each other. So I got 3 minus x equals 4x minus 8. So then I'm going to subtract 3 from both sides, and I'll also simultaneously subtract 4x from both sides like so. Boom. And negative 8 minus 3 is negative 11. On this side, I have negative x minus 4x is negative 5x. Divide by 5, negative 5, I should say, and we get 11 over 5 because the negatives will cancel out. So then we can look at this and say, hey, is this going to be legit? Over here, 3 minus 11 fifths. I know it's going to give me a positive value, so that's looking good. Over here, we'll have 44 over 5, which is just a little bit over 8. So that minus 8, that's going to be legit as well. So now we're going to graph this in Desmos and verify that the answer is indeed 11 fifths, which should be 2.2. So let's check it out. So here are the two graphs, and we can see the intersection just like we predicted occurring at x equals 2.2. So 11 fifths or 2.2, same thing. Boom, done. So for this one, I'm going to start off by using the change of base formula because I want to get every logarithm to have the same base, which I have 10, and then here I have this log base 2, but I can get around that. So I'm going to show you how we're going to do that. First, I'm going to take that 3, and I'm going to rewrite that 3 in terms of log base 2, the same as what we have in the denominator. So log base 2 of what equals 3? It's basically saying 2 to the third power is what? It's 8, okay? So, because again, this asks the question, 2 to what power is 8? It's 3. So I can rewrite it like this, then that denominator stays the same. Now my change of base allows me to go backwards and say log base 2 of 8 or log base anything of 8 over log base that same thing of 10 can be rewritten as log base, and then the big number 8 goes on top, and that the bottom number goes in as the base, as the little number. So we can say this is the same as log base 10 of 8 or log of 8, right? Just we can write it like that. And now I have minus log, again, base 10 of x minus 9 equals log of 44. Now I can consolidate these because they're the same logs and their subtraction. So that turns into a quotient situation. It's the first argument over the second one, like this, equals log of 44. Now I have log equaling a log, and it's the same bases as well, so I can just set the arguments equal to each other. Now I can multiply both sides by that denominator. 8 equals 44x minus 9 times 44, which is 396. Then I'm going to add 396 to both sides, and I get 44x equals 404. Last step, we're going to divide both sides by 44. And dividing the top and bottom by 4, we can simplify to, we don't have a lot of room here, but 404 divided by 4 is 101. 44 divided by 4 is 11. So there it is. Now let's verify this in Desmos. So here we have the two functions being graphed, and we can see the intersection is at 9.182. And just so you can see, this is the same value, right? 101 over 11. So we'll round it to 9.2 to the nearest tenth. So 101 over 11, or 9.2 for the approximation. Boom, done. So for this one, it says an account with an initial deposit of $6,500 earns that interest compounded continuously. And then it says how much will the account be worth after 20 years. So let's set this up with that continuously compounded interest. So we've got the amount in the account equals the principal times e to the RT. And the account will be, and then principal is 6,500. E, the R is 0.0725. It's that interest rate in decimal format. And then it says, how much will it be worth in 20 years? That's the T, that's the time, so we plug in 20. So when you plug it into the calculator, you get 27,710.24. So this should be the answer, but now let's actually graph this in Desmos. So here's a graph of the situation. We're trying to figure out what is the value of the function when we're at 20 years, aka when x equals 20. So now you can see that intersection point, and it gives us the same thing that we got from our calculation of the equation of this expression, 27,710.24. So now it's been verified, boom, done. So for this one, it says the population is modeled by this equation where t is measured in years, and approximately how many years will the population reach 20,000? So we're plugging 20,000 in for p, and we're solving for t. So the thing is, we've got an exponential variable. So we already know off the bat that in order to bring that down and solve for it, we're going to need to use logarithms. So we're going to start by dividing both sides by this coefficient in front just to simplify. So as we simplify that, we get roughly 400 over 33 equals e to the 0.5t. Then I'm going to take the natural log of both sides because I got a base of e. That just makes it easier because natural log of e becomes 1, and this exponent just comes down using that power rule. So now I have 0.5t equals ln of 400 over 33. And then last but not least, I'm going to divide both sides by 0.5, which is the same as multiplying by 2. So that means my t value is 2 times ln of 400 over 33. So we'll get this decimal approximation next using the calculator. So when we plug it in, we get about 4.98. So if we round up to the nearest tenth, it'd be about 5 years. Okay, so there we go with 5. Now let's graph it in Desmos and let's see where the intersection point is. So here we have our graph of the exponential equation, and then we want to know when the function value hits 20,000. So I said y equals 20,000, and then the intersection point is like we predicted, right? 4.98 or 4.99. Again, rounded to the nearest tenth is 5. So we verified 5 years, done. So for this one, they want us to rewrite it using the natural log. And the cool thing is if we want to just immediately convert it to its logarithmic equivalent, it's always log base that value, right? Whatever is getting raised to a certain exponential power. So log base e of the number on the other side, which is 17, equals that exponent, which is 5x. The cool thing about log base e is it is the natural log. So this is really saying ln of 17 equals 5x. And then to further isolate, we just divide both sides by 5 like so. And now let's use Desmos to get our decimal approximation. So here we have 0.5666, so rounded to the nearest thousandth is 0.567. So we'll say rough approximately 0.567, or this as the exact answer, done. So for this one, we're using the common log, meaning log base 10. So I'm going to start by taking log base 10 of both sides. Now taking the log of the left-hand side allows me to bring the exponent down as a nice coefficient. So now I have 4x minus 5 times log of 3 equals log of 38. Now I can divide both sides by log of 3. So I have 4x minus 5 equals log of 38 over log of 3. Then I'm going to add 5 to both sides. And last step, I'm going to divide both sides by 4. So I get x equals log of 38 over, since I'm dividing by 4 log 3, and then plus that 5 is also divided by 4 as well. Now in the back of the book, what they did is they made these have common denominators. They did that by multiplying this by log of 3 over log of 3. And then they consolidated into one big fraction, which I'll do here just so you can see how they got it in the back of the book. And then it's just log 38 on top, and then plus 5 log 3 as well over that single 4 log of 3. And then again, that's base 10, right, for all of these. So there you go. Now we're going to plug it into Desmos and get the approximation. And we get 2.0777, so rounded to the nearest thousandth, 2.078. So we'd also say approximately 2.078. So there are your answers. Boom, done. So for this one, I'm going to start algebraically, and then once we get our answer, I'm going to plug it into Desmos and approximate to the nearest 10,000th. So first, I'm going to subtract by 7.9 from both sides, and I get 7e to the 3x minus 5 equals 39.1. Then I'm going to divide both sides by 7. I get e to the 3x minus 5 equals 39.1 divided by 7. Then I'm going to take the natural log of both sides, okay? And this is great because this essentially destroys that, allows me to bring that exponent down as a coefficient, but it's times 1 because ln of v is 1. So then we have 3x minus 5 equals ln of 39.1 over 7. Then we're going to add 5 to both sides. And then last step is I'm going to divide everything by 3. So we're going to plug this into Desmos and get a nice approximation. And once we plug it in, we get 2.24007. So rounding up, we get approximately 2.2401. And there's your approximation, done. For this one, we're going to start by consolidating these two things on the right-hand side. So how can I do that? Well, one, I want to write that as log base 10 of something because I got log base 10, right? Well, that's nice because 1 is always log base 10 of that same base, aka log base 10 of 10, plus 5 log of 5, so on and so forth. So now I can do some other nice things, right? I can use the power rule sort of in reverse. I can take this coefficient and make it a power of this. So now I have log base 10 of 10 plus log base 10 of 5 to the 5th power, which is 3,125. Now I can use my addition rule when I have the same base, where I'd multiply these arguments. So now I have log base 10 of 31,250 equals log of all this. And now since I have log and log on both sides and it's the same base, I can just set the arguments equal to each other. Then I'm going to add 9 to both sides. And last step, we're going to divide both sides by negative 0.7, and we get x equals 31,259 over 0.7, and it's negative, right? Now let's plug this into Desmos and get a nice approximation. And we get negative 44,655.714, and we'll make that 3 because we're going to round up with the 8. So we have negative 44,655.7143. So there are your answers. Boom, done. So for this question, we're talking about magnitude of an earthquake, and we're given this equation, and they're also letting us know that this constant has this value. And then what they're asking is, what would be the magnitude, meaning m, of an earthquake releasing this amount of energy? And that's your E value on top. So we're literally just plugging and chugging. So on top, we have 1.4 times 10 to the 13th. And then on the bottom, we have E null, which is 10 to the 4.4 power. And all we're doing is we're going to plug this into Desmos, and we're going to get a nice approximation. So when you plug it in, you get 5.83. So the magnitude would be 5.83. Boom, done. So for this one, we're basically just meant to isolate t using properties of logarithms. So let's do that now. So first I'm going to divide both sides by a, and I get y over a equals EKT. And again, I'm trying to isolate t, but it's a variable stuck in an exponent. So to bring it down, I'm going to have to use logarithms. And in particular, I'm going to use natural log because I've got this as an e raised to a power, and natural log of e cancels out to 1. So first I'm going to bring down my exponent as a coefficient. So it's going to be kt times ln of e, and ln of e is 1, so we're good to go there. Then my last step is I need to divide by k to isolate the t. So I have t equals ln of ya, and then divided by k, or times 1 over k. Now the thing is, they wanted this as a single logarithm. So the one thing that you could do after this is, since you have this as a coefficient, you can move it back as a power of the logarithm. That's allowed. So that will be their nice single logarithm. So it's ln of y over a to that power, to the 1 over k power. So we'll put that in the second bracket. There you go. Boom. Done. So for this question, we're talking about Newton's law of cooling, and basically what they want you to do is isolate T, so we're going to do that now. So first I'm going to subtract both sides by Ts, and that equals T null minus Ts times e to the negative kt. Then I'm going to divide both sides by this coefficient. Now once we're at this point, I'm going to take the natural log of both sides like so, and natural log of e is 1, so that's beautiful because I can bring this down as a coefficient, and the natural log of e is 1, so that just basically goes away. So now I have ln of t minus t sub s over t null minus t sub s equals negative kt. Now I'm going to multiply both sides by the reciprocal of negative k. So now we have this, t equals negative 1 over k times ln of t minus t sub s over t null minus ts. And then I can use the coefficient rule to turn this into an exponent of this argument. So the final answer is t equals ln of t minus ts over t null minus ts to the negative 1 over k power, like so. Boom, done. I hope you guys enjoyed this video, and if you did, please click that like button. And if you want to see more from the Scalar Learning channel, make sure to click subscribe. Thank you guys so much for joining, and I'll see you in the next video. Take it easy.